Okay, so today what we have going on is we're going to start our proof chapter. And so we're going to talk about how can we logically look at information and talk about it. And so one way we're going to speak about it would be inductive reasoning. So inductive reasoning starts with the letter I. And so you think about this, the I is a point, okay? And so inductive reasoning starts with a lot of points of data. We're going to say, oh, like if you walk around the halls of Olathe South, you see a lot of people, a lot of points, a lot of thinking about. You can try to generalize, oh, I noticed that. And you can make a conjecture, a logical thought to say, hey, to summarize what you notice about your data. And so let's talk about this just a smidge. Okay. So inductive reasoning, I'm going to use a highlighter instead of just pen. So inductive reasoning is the process of reaching a concluding statement based on a pattern of examples. So if you walk around Olathe South and you look at people and you're like, I noticed that most of the people are nice, or you can try to generalize about what you see. Now, a lot of times we look at numbers and like, oh, I noticed that the trend is it's increasing, etc. And so you take some specific examples and you generalize and think to see, can you summarize or make a concluding statement based on that? So your concluding statement would be a conjecture, okay? And you would say, oh, this is going to be what I noticed about my examples, okay? And then the thing is, it may or may not be true always. Okay. So you can say, hey, I noticed that people are nice. Well, if you talk to anybody, you're like, well, I noticed this one person who they're just mean all the time. And so a counterexample say, not everybody is that way. Here's an example that shows it's not always true. Okay. So you can't prove to say, hey, I noticed this. Here's kind of a generalization about what I noticed. And you can't prove it, but you can say, it's not always true by showing a counterexample. Okay, so you can't prove it, but you can say, in general, I noticed this, but you can disprove it by saying, here is a counterexample that shows it's not always true. Okay, in fact, it's actually false. Okay, because even if you find one counterexample, it is not considered true. Okay, so that's something good to know. So to demonstrate that it's true, we would normally just do a specific deductive reasoning, okay, logic. Okay, so that's the other side of this. So inductive means you just kind of generalize and make a conjecture about it, and you can't prove it, but you can show it's not necessarily always true by a counterexample. Deductive reasoning, okay, is what lawyers use. Okay, if you're in debate, okay, you might talk about deductive reasoning where you say, I'm going to use facts, rules, definitions, properties, and you're going to talk about conclusions from the statement. So if you're trying to be a lawyer in a court of law, you're say, my client, this is true, and here's why, here's another thing that's true, and here's why. And so therefore, my client is innocent, and so you're trying to show by facts, rules, definitions, properties, and reasons to show why something is true. Okay. And so there's something called the law of detachment. So if P goes to Q, okay, if P then Q, then if P happens, then Q will be the result. Okay. So an example would be if you have a job and work there, okay, then you're going to get paid. And so that could be an example of if P then Q. Okay. If a car is out of gas, that's the if, then it will not start. Okay. Your car's out of gas, well, then therefore it will not start. So inductive is just looking at examples and trying to generalize what you see. Deductive is specific logical steps, rules, definitions, properties. And this is what we're going to do when we actually do proofs. Okay. So you can make statements, and the truth is they may be true or false. Okay. If walk under a ladder, it's bad luck and you're going to always have bad luck. No, if you break a mirror, no, that's not necessarily true. Okay. And so there are statements and they could be either true or false. The truth value is, are they true or false? We could make just general statements like, if you do this, then that's a result. That's a statement, but you can also do compound statements where there's two things. If you have a compound fracture, it means not only do you have a broken bone, but it's sticking out of your body. Okay. A compound fraction is fracture on your body is not only do you have this, but also there's two things going on that are a problem. So a compound statement, let's talk about this. A compound statement is when you have two things going on and they might have an and or they might have an or. What do you mean? Well, an and means that you have to do both this and this. Okay. Like if your mom says you have to do chores, this and this, you got to do both. Well, to have a square, you have to have four congruent sides and four right angles. If you just had four right angles, you might just have a rectangle. But if you want to have a square, you need four congruent sides and four right angles. Okay. The or could be you could have one or the other. Okay. If you want to attend Olathe South, you could be a student, or maybe you could be an employee, or maybe you could be both. Okay. And so like maybe you get paid to be a student. So that'd be great. But and means you have to have both, or means one or the other, or you could have both. So and must means you have to. Okay, so and there's symbols that represent the and is an N and or is a V. Okay, so okay, so let's talk about inductive. We're going to go back to inductive reason. That's what we're going to focus on today. Inductive means look at samples and make a conjecture about what you see. Okay, so that's going to be what we focus on today is inductive. We're going to move to deductive later on the chapter, but we're just kind of starting with inductive today. So notice here's a list of numbers starting at 8. What happens between each number? Okay. And to do a conjecture, you always say, put where you start. Start at 8. Because we don't know. This might be you get paid every time, this happens. Or this might be you switch hours, every time this happens. So it starts at 8, we know. We don't know if it goes before that, but it starts at 8. Then add 1 hour, 30 minutes each time. Okay, so that would be your conjecture. Okay, notice this is a pattern. We're not proving anything, we're just noticing that's what's happening. So if this pattern continues, your next item would be 2 p.m. Okay. All right, the next one. Notice there's a pattern here. Okay, there's a sequence of, a sequence of values, and start with a star. With top shaded. Okay, and then what are you doing? What would be the next star? So if you draw Patrick, which of his arms would be shaded in? Okay, and it looks like, let's see, dun, 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 dun. It would be this one right here. Rotate counterclockwise. How much? Well, you're rotating one star, isn't it? Okay, one little notch. Okay, and there are 5 notches, and a whole circle is 360. So if you do 360 divided by 5, you get 72 degrees. Okay, so you're going to rotate your star 72 degrees counterclockwise. Okay, so let's keep moving. Okay, here's these numbers. Okay, if you notice, start with 100. And what are we doing? We are dividing by 2. Okay, so divide by 2 each time. Okay. This next one, the next item would be 3.125. Looks like I was trying to jam this on one sheet of paper. So it looks like these guys go together. Okay. Okay. So that's the conjecture. You're going to try to say, starting with this is what you do to make the pattern. Okay. You're noticing the pattern. We're not proving anything. We don't know if it starts earlier or goes further, but we know there is a pattern with the values that we see. Okay. So let's make a conjecture about what we see here as well. Okay. The sum of an odd number and an even number. Okay, what happens if you take an odd number plus an even number? Sum means add, product means sum. You should know these things. That's a good thing to hold on to. If you take an odd number plus an, so like that would be 5 plus say even would be 6. Okay, you get 11. Okay, let's try it again. See what else happens. Say an odd number would be 3, and add an odd number or an even number to it, 6. That makes 9. Well, it looks like we're getting an odd number. Okay, the sum of odd and even gives an odd number. Okay, so you're making a conjecture. We're not proving it, okay? We're just saying what we notice, okay? The product of 2 odd numbers, okay? You take 3 times 5. You get 15. What about 7 times 3? 21. 9 times 3. 9 times 6. Okay, 54. Let me see. Oh, I was like, why is that different? Where's the odd number? 6 is not an odd number. I'm like, what's happening here with math? Did I multiply it wrong? No, I just wrote down not two odd numbers. Let's do 5 times 7. That's 35. Okay. So our conjecture is the product of two odd numbers is odd, sorry. Struggling. It's getting late. Okay, so that would be our conjecture. We're not proving it. We're just saying in general, that's what I noticed. Okay, if you find something that makes it not true, well, then that's a counterexample and you just disproved it. So you can by example show there is a pattern here, but even one counterexample will disprove it. Okay, so let's keep going. Okay, let's find some counterexamples. Okay, so if I say, hey, here's my conjecture. Everybody at Olathe South always wears blue and yellow. Give me one example of a person who does it, and you found a counterexample, and you've blown my theory out of the wall. It is false, okay? So our complementary angles, do they always have a sum of 180 degrees? Okay, no, that's false. Why? Complementary angles, 30 and 60, 30 plus 60 equals 90 degrees. Okay, that's what a complementary angle would be. So give an example of something that disproves that, okay? If you multiply 2 times a number, you'll get an even answer, okay? So is that true or false? Can you come up with a counterexample that makes it false? 2 times any number. Nothing I can come up with. 2 times any number will be an even value, okay? So I can't come up with a counterexample. Okay. Not collinear points must lie on the same line. So if you got A and B, you want something that's not collinear with it? C. No. A and B, A, B, and C are not collinear. And guess what? They don't lie in the same line. Okay. Collinear means you can't make a straight line with them. So therefore, will they lie in the same line? No, they're not going to lie in the same line. So come up with an example that shows that's not true. Okay. Everybody out of Olathe South is nice. Come up with one mean person. You're like, nope, I just showed it was wrong. Okay. If you can't come up with a counterexample, then it's considered true. Okay. You're not proving it. You're just saying it's probably true. Okay. So let's look at a pattern. We're talking about Amy is collecting data. How many kids don't turn in their homework? So in week 1, so this is week, there are 5 kids. Okay, so 5 students who didn't turn in the homework. Week 2, there are 8 kids who didn't turn in their homework. Okay, week 3, there were 12 kids who didn't turn in their homework. Week 4, there were 17. Okay, if this pattern continues, how many students will not turn in their homework in week 8? So 5, 6, 7, and 8. Okay, see what the pattern is. I notice this is plus 3. This is plus 4. Okay, this is plus 5. Oh, I can tell the pattern. You would plus 6 here to get to 5. That'd be 23. You would plus 7 again to get to the next one, and you'd get 30. If you plus 8, okay, you get 38, and then plus 9 would get you the next one, which would be 97. So actually, I don't know why I said 47, probably because I can't read my handwriting on my note sheet I'm looking at. That would be 47 kids. Okay, so you're basically saying, can you make a chart? Can you say, at this week, there are this many people? And then see what pattern is and follow it to get to the week that you want to know. Maybe they'll ask you for the total. Maybe they'll ask you for how many in that week. Just read the directions. Because I think I've seen stuff where they're like, how many total kids in all the weeks would there be? So you have to add all those up. So just watch to see, can you read the words that they're asking you to do? Okay, a Venn diagram is a visual display of what is happening in a group. So if I say, I want you to be in this and this, okay, the rule is this. It is just the overlapping portion. What do you mean, woman? Let's look. Well, my diagram did not copy. So let's get this on here. Okay, so we've got 3 circles. Be careful when you draw these, okay? They should look just like this. Okay, this one should say tap, okay? This one should say jazz, and this one should say ballet. And it does look like the only number that copied would be the 6 people are in neither, and none of those 3. Okay, so there's 6 kids who are not in tap, ballet, or jazz. Okay, maybe they're not dancing at all. Who knows? Okay, so tap. Let's look at anyone who lives in the tap circle is in tap. So like 28 would be the people in tap. Okay, who are only in tap. Okay, there are a couple people who are tap and jazz. So this would be 13. And then there are 9 kids right here. Okay, and then there's 17 here. Okay, so if we want to answer the question, how many kids are in TAP total? You would add up all these kids right here. Okay, and I'll see if they didn't ask it. Okay, the total TAP would be 28 plus 13 plus 9 plus 17. Okay, the total kids who are in jazz would be, let me add into these numbers. This is 43. This is 25. Okay, so the kids who are in jazz would be anybody who's in the jazz circle. Now, if you want to say tap and jazz, okay, it's only in the overlapping portion of tap and jazz. Okay, so who's in the overlapping? Because notice the 13 and the 9 are in the tap circle and they're also in the jazz circle. So 13 and 9 would be the kids who are in both tap and jazz. Okay, the overlap. Okay, do you see how they're in both circles? Okay. Now, if I say tap or jazz, if I say or means it is both groups and the overlap. So it'd be one or the other or both. Okay. One group or the other or both. Okay. So if I say who is in band and in Spanish, you'd have to be in both to raise your hand. If I said band or Spanish, you could be band or Spanish or both. Okay. And so or means one or the other or both. Okay. And so let's talk about this. Tap or jazz means you could be in tap. Okay. You could be in jazz or you could be in both. And so that would be all the numbers here to be like 28 and 13 and 9 and 17 and 43 and 25. And that total, I believe, is 135. So or means one or the other or both. Okay. All right. How many are enrolled in all 3 classes? Okay. Do you see anybody who's standing in all 3 circles? Because we haven't talked about the ballet. Okay. I'm going to make that ballet pink. So anybody who's in the ballet circle is going to be in ballet. Now they might also take other classes because if you're in ballet, you probably do take other classes. 27 kids are just in ballet. They don't believe in tap and jazz and everything else. But who's in all 3 classes? And that would be like an and. Okay, they're in tap, jazz, and ballet. Well, the people who overlap in those 3 things would be 9. Okay. How many kids are not in any class? Well, that'd be 6. Notice they're not in any circle. They're sitting out. How many kids are in tap or ballet? Okay, tap or ballet means you're in tap or ballet or both. Okay, so let's do that. So it'd be 28 and 13, tap, ballet, or both. So 17 and can't tell if that's 4 or 9. That's 9. And then 13, 17, 25, and 27. I believe that total is going to be 121. 121, not 125. So let's fix that. Okay, 121. So if I say tap or ballet, you do anybody in tap or anybody in ballet or both. They could even be in jazz and they might even own a tuba. Who knows? Who really cares? Okay, tap and ballet. Okay, tap and ballet is going to be, let's see if I can get rid of that. Well, there we go. Tap and ballet would be the overlap between tap and ballet right here. Okay, so tap and ballet. Okay, so these two things right here. If you're tap and ballet, you're in those two sections. So it'd be 9 plus 17. Okay, and that would be 26. And means it's got to be in the overlap between those two circles. Well, who's in tap and ballet, but not in jazz? Okay, well, that would just be 17. Okay, because you see how 9 in the middle are going to be in tap, ballet, and jazz. They just want tap and ballet, but not jazz. Okay, so that'd be 17. So these are good questions, and implies they're in the overlapping region between the two places, or implies one or the other or both. So that would be how you kind of talk about those. Now let's talk about inductive versus deductive. Inductive means sampling and making conclusions. Deductive means using laws, logic, definitions to basically prove what's going on. So that's what like attorneys would do. Like, therefore, you owe my client $1 million. Okay, so it's kind of a lucrative situation. Okay. Bob is, so if you return a library book, you're going to be charged a $2 late fee. He returned it late, so therefore he is charged a late fee, and this is going to be deducted. He used laws and regulations, okay, to help see it. Andrea notices every single time she wears her favorite jersey, her team wins. Sorry. And Andrea is wearing a new jersey, so she concludes that her team will win. That is inductive. She's just sampling to say, hey, I noticed this happens. It's a generalization. I'm trying to come up with a conjecture. You can't prove it, but you can say it normally happens. You can disprove it by a counterexample. Okay, the one time she wore it, but they still lost. Okay, Newton's laws of motion. Object at rest will remain at rest. That is going to be deductive. And the last one, Miss Jackson notices that her data usage is increasing by 2,500 megabytes every month. So she calculates that she thinks that's going to continue. Okay, that is going to be inductive. She's doing a sampling and noticing patterns and saying, I project this is going to happen. She's not proving it. She doesn't know for sure. And who knows if there's a limit to how much it'll grow. But she's noticing at this point in time, it keeps increasing. Okay. All right. Well, that is what I have for you today. We talked mostly about inductive reasoning. We introduced it deductive, but we will do more of that when we get more into proofs. All right. So thank you so much. Have a good day.